Hello, welcome to another video. So in this video what I plan to do, or hope to show you how to do, is actually work through some of these one-dimensional kinematics examples. And we're going to be using kind of the problem-solving techniques I talked about, as well as the 5 equations to actually do some of these. So let's look at this first example. The position of a runner as a function of time is plotted as moving along the x-axis of a coordinate system. So during a 3-second time interval, the runner's position changes from x equals 50 meters to x equals 30.5 meters. And we want to know what is the runner's velocity during this. Okay. So because we're just doing 1D to get your feet wet, and it's very clear this is the x-axis, when we're doing step 1, right, which is like understand the problem, I know that what I'm going to do is I'm going to set up an x coordinate system here, and I'm going to set up, with my drawing, I'm going to make the right positive, okay? Most of the time we're going to do this, like this is a standard system, but here especially it makes sense to do, okay? So I'm going to just draw a little runner, give him a little happy face, and I'm going to say, it says the runner's position changes from x equals 50 meters, so here's 50 meters, okay? And then he goes this way, and then he winds up at 30.5 meters, okay? And of course, zero's over here. Whoops, that is 30.5 meters, okay? All right, so that's step 1. I've drawn the problem. You may want to say off to the side, because there is a 3-second time interval, you may want to just say t equals 3 seconds and list other information in the picture, like what is velocity. And so now when I look at this, when I look back at the problem, when I'm setting it up, or when I'm trying to solve it, when I do the next step, I don't have to go back and read the question, okay? Like I said, I don't really tend to draw every single problem that I do, but I am going to do it here just so you see what's going on. And I will draw the more complex ones as well. So step 2 was knowns and unknowns. So if you remember, knowns and unknowns was basically everything we know about the problem and perhaps everything we don't. So what I do is I go through and I look for position, velocity, acceleration, and then time. And I usually do it in that order. And then I do anything else. So the position, because we're just looking at one dimension, it's just x. So we look at x initial, okay, that's our known. We say, well, our x initial was 50 meters. That's where he started. And you may actually, when drawing this, I should have probably labeled this as x initial, and this being x final, just so it's really clear. So this is x initial equals 50 meters. We also know x final is 30.5 meters. That's our position. So we're done with position. We can cross that off. We can move on to velocity. Do we know our velocity? Do we know v initial? Do we know v final? We do not. We don't know any of those. We just know there's a position change. We don't know v initial. We don't know v final. We do know, though, that v initial equals v final. And I say this because we're not told so I'm just going to call it v, okay? Because we're not told that the velocity is changing, okay? And if we aren't told the velocity is changing, this also tells us our next thing, which is acceleration, we know is 0. Okay? So you go through, you do position, velocity, acceleration. The last thing is time, and we're explicitly told the time is 3 seconds. Okay? You can write time as 3 seconds, or you can write, t initial is 0, t final is 3, or you could just do t, which is implied to be delta t, being 3 seconds. This is usually what I opt to do because t initial most of the time is 0, and so you don't need to explicitly say it each and every time because you're just going to cancel it in the equation. Okay. So this is it for our knowns and unknowns. It's very clear. We know the position, we know the acceleration, and we know the time. We don't know our one velocity. This is what we're trying to find. There's nothing else that we need to talk about. So we can move on to the next step. Step 3, equations. Okay, so we need to pick an equation that makes sense. We have several equations to pick from. We have x final equals x initial plus v naught t plus 1/2 at squared, and we have v final squared equals v initial squared plus 2ax. These were all the equations. Now, we don't know velocity. So we don't know this, okay? But we do know x, a, and t, okay? So anything that links knowns to unknowns is something we should look at. So let's look down here. We don't know velocities, okay? But these would be the same. This equation doesn't work because these guys are the same value, and so it doesn't work for us because a is 0. This equation actually tells us nothing here. Because a equals 0. Here, this a is 0, so it would cancel out this guy. Okay, so 1/2 times 0 is 0, right? So this entire thing would be gone. This would leave us with x final, x initial, and v naught t, which, if you look, is the exact same as this formula. Okay, so this actually looks promising because it allows us to solve for a velocity and keeps x final, x initial, and time. So we can actually probably use this guy. But just to show you further how this works, let's go to the next one. This guy again, a is 0, so this goes away. And this just tells us v final equals v initial, which is what this one tells us. So this equation doesn't work here either. This one doesn't work either. It relates velocity to itself. It's not really useful for us. So again, this just tells us v equals v. Great. Nothing. So we can actually probably use this equation. And again, I think we can use this equation because we don't know this guy, we know this one, we know this one, and we know this one. So we know everything but one thing. So one equation, one unknown. And typically that's how it will work with these sort of problems. The number of equations need to match the number of unknowns. If you have 2 unknowns, you need 2 equations. If you have 3 unknowns, you need 3 equations. We only have 1 unknown, so we just need 1 equation. So let's move on to step 4, solve. Okay, so x final equals x initial plus v naught t. X final was a 30.5 meters. If you look back at our known and unknown table here, 30.5. X initial was 50 meters? Let me just go back and look. 50 meters, okay. Plus V, so V naught equaled v final equaled v, if you remember. So I'm just going to go ahead and replace that variable now, just to not be ambiguous anymore. But you can certainly leave it because they're all equal. And then the time was 3 seconds. Okay, so now we need to solve for v. So 30.5 meters minus 50 meters equals v, 3 seconds. This was minus 19.5 meters. I can't do the math, but yes, 19.5 meters equals v times 3 seconds. So v during this exchange is 19.5 meters over 3 seconds, which is minus 6.5 meters per second. Okay, so step 5, check solution. So here's my check. Here's our solution. Does this make sense? Well, we have the right units. Check. So right units. Velocity is in units of meter per second, so that works. The other thing is this negative right here. Does this make sense? Well, we define to the right as positive, and the guy is moving to the left. So yes, negative makes sense. Okay, so this works. Solution seems fine. Okay, and that's how you solve a one-dimensional problem. Okay, let's go ahead and do example 2 next. So for example 2, we have this question. An automobile is moving to the right along a straight highway, which we choose to be the positive x-axis. Okay? And it says, then the driver steps on the brakes. If the initial velocity is 15 meters per second and it takes 5 seconds to slow down to 5 meters per second, what was the car's average acceleration? Okay. So we need to draw this first. Okay? You don't have to, but I choose to. So it is moving to the right along a straight highway, which we choose to be the positive x-axis. So it straight tells us to do this. Then it says the driver steps on the brakes, and it has an initial velocity, and then it has a slower velocity, and then it wants to know this. So what it's telling us is, here's the car, and it's moving to the right. Okay? And it says it's moving to the right, v initial equals 15 meters per second. And then what's happening is it's slowing down, and it's saying v final equals 5 meters per second. Now, when it slows down, that means that we have an acceleration to the left. So we don't know what the acceleration is, but we know it should be negative. So okay. So we'll just kind of pocket that information for later. The time it takes is 5 seconds. Okay. And I guess I don't have to dot that guy in. I just wanted it to be clear that this is final state. Okay, so let's go ahead and do knowns and unknowns now. That's the second step. So, x initial. Do we know our initial position? No. Do we know final position? No. Nowhere does it tell us that. We can define, actually what we can say is we can define where the cart is initially to be its initial position. So we could just define this as 0 and say x initial equals 0. So let's go ahead and do that, just in case that will be helpful to us. But it doesn't really tell us anything about position. X final, we of course have no idea about. There's no information. And we can't define anything for that. Other than that, so we define this. That's it for position. Now we'll move to velocity. We have initial velocity and we have final velocity. Okay, now we can do acceleration. We don't know it. What was the car's average acceleration? It's a question. This is what we need to solve for. Time, we know it. It was 5 seconds. Okay. So we need something that will link acceleration with time and probably velocity. So looking at our current equation list, I think there's two that have velocity in them. There was this guy. The problem with this guy is it links position, and we don't know anything about final position, so we probably can't use this one. But there was also another one, which was this equation. V final equals V initial plus AT. I think this works because we don't know acceleration. We know this, we know this, we know this. So let's use this, okay? Now we need to solve for A. So V final equals V initial plus AT. I should mention at this stage, most students go ahead and probably plug in numbers. I usually don't. I did on the first one, but I'll solve for the variable first, and then I plug in numbers. And the reason for that is it's easier to do. There's less calculations you end up doing over time for longer problems. And if you were asking multiple questions about this, like say you had multiple velocities and multiple times and you wanted to know what the acceleration would be in all of them, you only need to solve the equation once instead of each time for each thing, so it's more generic. And it does have advantages. That said, doing it this way ends up being more algebra, and so a lot of students prefer not to. I'm not going to force you to solve anything in a particular way. That's up to you. So I'll subtract that over. But I will say this ultimately ends up being the superior method when you get really comfortable with the math and the algebra. Go ahead and move T over. I should mention this right here is the definition of acceleration, right? But that's because we got it from this equation from the definition, so it makes sense we'd get it back. Okay, so V final, I believe, was 5 meters per second, and our initial was 15, and then our time was 5 seconds. V initial 15, V final 5. Cool. This is our A. So 5 minus 15 is negative 10. Oops, not 110. This is over 5 seconds. This is A. This will result in meters divided by seconds divided by seconds. That will give us units of meters per second squared. And then 10 over 5 is 2. So 2 meters per second squared. So now checking our solution. We have the proper units. Looks good. And then this minus 2 right here, we claimed up here we need a negative answer because we're slowing down. So our acceleration should be negative. And it is. So looks good to me. Yeah, looks good. So let's go ahead and do another example. Example 3 is up next. So you were Here it is. You're designing a small airport for small airplanes, or an airport for small airplanes. One kind of airplane that might use this airfield must reach a takeoff of at least 27.8 meters per second and can accelerate at 2 meters per second squared. If the runway is 150 meters long, can the airplane reach the required speed for takeoff? And if not, what minimum length must the runway have? Okay, so this right here is the most difficult problem yet, and that's usually how I structure my examples, is I increase in complexity every time we do something. That said, you still do the same processes, okay? So this is still a one-dimensional problem. We're still going to define to the right as positive. We'll start the airport at 0. We know by the end of this thing, it needs a V final. V final needed to take off needs to be 27.8 meters per second. But we ultimately, for part A, can this airplane reach it? So we don't actually know. So what else don't we know? Or do we know? We know 2 meters per second squared, so we know our acceleration. And we know the runway is 150 meters long. And this was our x initial, which we define. I guess small airplanes, I might as well actually draw one. Let's see. That looks like a good airplane, right? One thing we know, V initial is 0 because it's starting off at 0 meters per second. This right here is an example of an implied value. It's not explicitly told that the airplane starts at 0, but it must if it's taking off, right? And so these are the kind of more difficult values to get. It's not obvious because sometimes you're like, should I make this assumption? I don't know. Something like this is an assumption you can make. If something's just starting moving, it doesn't have an initial velocity. So we're going to take our picture and take our understanding of the problem and put it into something we can use. Knowns and unknowns, like always. And I'm going to actually make the distinction here, part A, because we do have 2 parts. And so we must separate it, or it's important to. All right, knowns and unknowns. Position. We defined 0 as the initial position like we always do. X final, we're told, is 150 meters. That's our position. What about our velocity? Well, we know, right, this one's implied. We're starting off at 0 meters per second because we're not told otherwise. V final, we don't know. Okay, this is what we're trying to find. We need the needed one, right? We know that we must have 27.8 meters per second to answer the question. Can this plane reach it? So we need to know, is this going to be greater or smaller than 27.8? But we don't know what the actual velocity is. A, so because we just did velocity, because we just did velocity, we need the acceleration, 2 meters per second squared. And the time, do we know anything about time? No. There's nothing here that implies time. So we don't know the time that this takes, which is different than the other problems we've done so far. So let's go ahead and find an equation that works. We need V final. So there's 2 V final equations. I'll start with this one and see if this works. We don't know V final. Great, it's already solved for. We know V initial 0. We know A, and we know X. Cool, we can use this one. All right, let's do it. So solve for V final. V final equals, well, I'll just rewrite the equation. Taking note that we can actually nuke this guy right here because it's 0. We need to expand this out into x final minus x initial, because remember this is a delta implied. X initial is 0 though. And so v final squared equals 2a x final. So v final equals the square root of 2a x final. So now we can plug in our values. 2 meters per second squared times our x final, which was 150. Now when we multiply units here, so this will be v final equals 2 times 2 is 4, 4 times 15 is 60, 60 plus the other 0 is 600. So this will be 600 meter squared per second squared, which is good because when we take the square root here, this will turn into meters per second, which is what we need for v final, okay, or for a v. So v final equals the square root of 600, which I don't know what that is without looking, and it's told 20, whoops. You can only do so much math in your head, like I did with the 2 times 2 times 150. But this is 24.5 meters per second. Okay? Now, is this greater than 27.8? Greater than 27, whoops. No. The plane won't reach the required speed. Okay? So, we need to do part B now. If not, what minimum length must the runway have? Okay, so now, part B, we need to restructure our knowns and unknowns. So now what we're doing is we're looking for the minimum speed that, or the minimum length that you need to reach that v final. So now we know v final. We know it's the actual one, 27.8. So we're going to set x initial. So we're going to go through, do position, 0. We start off at 0 like we always do. Our unknown, this is what we're trying to find. How long must the runway be? V initial is still 0. V final now, we know. And we know this is going to be the minimum, 27.8. Because this minimum ties to how long this will be. Some number greater than 150 is what we're looking for. Because 150 didn't cut it. The A, the acceleration of the plane, is still the same. So A equals 2 meters per second squared. And we still don't know time. Okay. Let's look at the equations. I'm going to start with the equation we used before because I think it will work again. And looking at it, it looks good. V initial can still go away. We're still solving for, well, we're solving for x now in this instance. But it still looks good because we know A, we know V final squared, we know one of the x's is 0. Yeah, looks good. Let's go ahead and rewrite, or just set us up. So solve. So I'm going to go ahead and just do this. So V final squared, I'm going to do similar to what I did last time. This guy's 0. This guy's 0. Solve for this. Oops. So V final squared over 2a equals x final. So x final equals the 27.8 meters per second squared over 2 times 2 meters per second squared. 27.8 squared is a really hard thing to know in your head. This is, oh, I don't write it. I just write the answer. So x final is equal to 130 meters. And if you're curious what the units are, we're squaring meters squared, second squared on top, divided by meters per second squared on bottom. These guys will cancel. 1 cancels here, and this will leave us with units of meters. So check the solution. Units, they check out, just like I said, meters, which is the units of length. The other thing we need to check is 193 bigger than 150, which didn't work, right? 150 wasn't the solution, and yes. So the solution checks out. Numbers look good. Everything's positive. It should be positive. It's longer than 150. Looks good. Okay. So that's example 3. So let's go ahead and look at example 4. In these one-dimensional problems. So everything's along the x-axis. First foray into kinematics. How long does it take a car to cross a 30-meter wide intersection after the light turns green if the car accelerates from rest at a constant 2 meters per second squared? So here's the setup. We've got an intersection. We've got a light hanging. Oops. Boom, boom, boom. I don't have green set up as a color. I don't know how to do where it's like not on, so I'm just not gonna do the other colors. Okay. And so we've got a car. Becoming more and more that looks actually like a really terrible car, so I'm gonna take off the trunk. Okay. So this guy's going across some intersection. And he's just starting off, right? So he's starting from rest, which means our V initial is 0. That's the first thing that actually jumped out to me. I always look for this word rest because it implies something's coming to a rest or starting. Or it doesn't imply it, it just tells you. This whole intersection, we're told, is 30-meter wide. So that means the x initial is 0. X final is 30 meters. Okay. And then, so that covers that information. Light turns green. If the car accelerates from rest, okay. Constant 2 meters per second squared. Okay. Great. So this is kind of all the information that we need. So let's go ahead and do this. Okay, so knowns and unknowns. X initial is 0. X final is 30 meters, 30 meter wide. V initial, we're starting at 0. We don't actually know how fast the car will be going once it's gone through the intersection, so we don't really know anything about V final. A is 2 meters per second squared. Time, we don't know. And in fact, times what how long does it take? Okay, so this is what we need. Okay, cool. Looks good to me. let's go ahead and try to solve this. So an equation, we need time. There's a lot of equations with time. Let's try this equation. We haven't used this one yet. I don't know if it works. It's just one that's popping in my head. X initial would be 0. V initial would be 0. 1/2 AT squared. We know A. We know X. Yeah, we can use this guy. Cool. Let's use this and solve for T. Multiply over the 2. X final. 2 times X final equals AT squared. We need to divide by A. We need to take the square root. Awesome. So the time is 2 times 30 over 2 meters per second squared. So the units in here, meter over meter, that'll cancel. We're going to get 1 over second squared. That will flip this guy back up to the top to give us units of second squared, which will be canceled by the square root. So we're going to get 60 over 4, which is 15. So 2 times 30 is 60. Oh, 60 over 2. Never mind, the 2's just cancel. Right? Can't do math. So it's the square root of 30 second squared. And the square root of 30 second squared is 5.48. T equals plus minus, because we're taking a square root, 5.48. Now, what does this mean? So if you look, when we're crossing this intersection, we're moving to the right, which we've defined as positive, okay? So when we're moving this way, the time that will elapse will be the positive 5.48 seconds. What this also tells us is that if we were to cross 30 meters behind us, or reverse time, basically, we would also cross that same amount of time. So you can cross that same amount, or cross that same amount of distance. You can cross the same amount of distance to the right or to the left. And that's kind of what these negative solutions always show us. But the real solution here, because we can throw that out, right? Because we're only concerned with moving to the right after 0, not what happens before 0 if we were to do the exact same thing. So the real solution is the positive one. And you'll often see this come up when you're solving for time. You'll see this come up all the time in kinematics, where you'll get a negative solution. But just go ahead and throw out -1. And that's usually the case, okay, where you throw out the negative time. I don't want to say always the case, because I can't think of all situations right now, and it's usually dangerous to say always. So I'm going to just say most of the time throw out the -1, but there could be a case maybe where you keep it, potentially. I'm not sure. But you can usually get rid of the negative answer. Okay, or the negative time. Let's go ahead and do example 5. So, what is the stopping distance for a car moving at 14 meters per second if your reaction time is 0.5 seconds and the car can slow down at a rate of 6 meters per second squared? Okay. So this problem is more complicated again than any other problem. Let me show you why. I'm going to first set up our little thing right here. The car, we're told, is moving at 14 meters per second. We have a reaction time of 0.5 seconds. And then the car slows down at a rate of 6 meters per second squared. So that means that A right here, and this will be a negative value because it's pointing to the left. Okay, so just, and here, our V initial is still 14 meters per second before we slow down. Okay, then we have a third time where the car has stopped. Okay, so at this point, at this V final, before we slow down. So we've got two situations is what I'm saying, two different time intervals. Where, so V initial at this state is 14 meters per second. We're traveling along. At 0.5, our V final here is 14 meters per second. Then we kickstart a new section where V initial is 14 meters per second still. Then it goes into 0. And you must be wondering, why do we need to separate it like this? So here, A is minus 6. Here, on the left side, so on the right side it was minus 6. On the left side, we have a V initial of 14, and we have a V final of 14, meaning A is 0. Now, we're going from 0 to minus 6, which means A isn't constant here. And if you remember what I was talking about before, we can't, at least with the tools we have, do non-constant acceleration. That's where the issue lies. Anytime the acceleration changes, we can't do anything about it. But we can do periods of constancy. Meaning, for this entire section, for this first 0.5 seconds, we can do A is 0, and we can cover this motion here. Here, we can cover this motion, but we need to treat them as separate problems, okay? So treat these separately, okay? So let's look back. We ultimately need, what is the stopping distance? Okay, so we need x. So what I'm going to do right here is I'm going to say x initial is 0. Okay. After 0.5 seconds, we don't know what x final is. So we'll call this x final 1. Here is x final 2. We also don't know what the ultimate distance is. Okay, so what I'm going to do is I'm going to solve for this section first, and then this section. So, knowns and unknowns, and this is for A equals 0, okay? X initial, we've defined as 0. Our unknown here is our distance. That's what we're trying to find. X final 1, I called it. We know our V initial is 14. And we know our V final in this first section is 14. And since velocity is not changing, our acceleration is 0. Okay? We're also told that. Our acceleration is 0, which means that these guys are the same. Time, wait, did we know time? Yeah, 0.5 seconds. Good. Okay. So goal for this section is to solve for x final 1. So let's go ahead and get our first distance before the car starts stopping. Okay, so we'll have a period where the car isn't braking at all, that reaction time. Then we'll have a distance that it goes while it is slowing down. So, x final 1, or here, let me just get a generic equation. So I'll start with x final. X final 1 this guy can work, I think, because we're solving for x final. We know x initial, we know v initial, we know time, we know this. Yeah, this guy will work. But let's see, because we often have a choice in physics, let's see if there's an easier equation we can use. Actually, no, wait. This is what we get. Yeah. If we use this equation, A is 0, which means this whole thing will go away, yielding this equation. Okay. So what I was doing before when I was looking at this equation, and I was seeing this little squared thing up here, anytime you have something squared in an equation, it's annoying to deal with. So when you're choosing your equation, you have a choice sometimes to avoid using the most difficult equations. So my advice to you is, even if you see an equation that works, if it looks like a really annoying equation to deal with, like as a squared, try to use a simpler one. Okay? And so I was like, well, this one's a simpler equation. And I was like, well, wait, what about the acceleration? I was like, oh, the acceleration's 0. But yeah, oftentimes, because of the way the kinematics equations are derived, it's going to be the same thing, even if you're taking a different path to get there. Okay, so you can solve problems in different ways. It's not unheard of. The reason, so if we're looking at this like, oh, maybe you didn't start with this equation, like maybe you wanted to use this one first. Oops, 2ax. What this one would tell us, because a is 0, if you were going this route, this would just tell us v final equals v initial, which we already know. So this one wouldn't even be worth it. The only other equation you could potentially use is this one, and you get the same issue. So we're actually, for this particular problem, we are forced to use this equation because a is 0. So now that we've made our choice, and I do hope that's not too confusing for you, just know that you have a choice in the equations that you use. And also don't feel, disheartened by the fact that, oh, I made a bad choice, now I have to go back and choose a new equation. It's not a big deal, okay? You now know a path that doesn't work. So just try the other equations and see if they work. Okay, that's my advice. Choosing the equation is some of the hard part of this whole thing, this whole process, as well as making assumptions. Okay, so we're solving for this, which this guy's 0, which I labeled as x final 1. So this is v initial times t, which v initial was 14 and time was 0.5. So the seconds cancel. We're left with 14 times a half, which is 7. And the seconds cancel, so we're left with meters. So this is our first distance right here. So this would be 7 meters if you were going back. So now what we can do is there's a couple ways you can solve it from here. You can treat this guy as an entirely new problem and set this new position at 0, and then figure out this distance, x final 2, and if you do that, you would have to add x final 2 to x final 1 at the end. I'm going to just treat x final 1 as our initial position in this new instance. So we're starting at 7 meters rather than 0. The advantage to the other method is that anytime you define your starting position as 0, you get to cancel another part of the problem, right? So we need x final, and there is an acceleration in this instance. So if we were using this problem, or this formula right here, we would have to deal with this because this would be a value. We don't know the time though. Yes. So we can't use this, we don't know time. For stopping section. So we can't actually use that. Another equation that has x final in it would be this guy. And you often want to use this equation when you know you're stopping, because stopping equals v final equals 0. Okay, this means this would be true. And I think I even labeled that v final is 0 at the very end. So whenever something's stopping or slowing down to 0, you may want to consider using this equation, because we'll get to cancel this guy. It looks like this equation works. It allows us to solve it without knowing time. So let's go ahead. This guy is 0, which means our equation is 0 equals v final squared plus 2a x final minus x initial. Okay, and we want to solve for x final. Okay, which remember in our instance is x final 2. So 0 equals v naught squared plus 2a x final 2 minus x initial. I'm going to move this guy over. Now, this is a squared value, which means if I were to plug in 10 here, okay, I would say v naught's 10. 10 squared is 100. You move 100 over, it would be negative 100 on the other side. So what I mean by that is, don't put the negative sign, don't square the negative sign away is what I'm saying. It's outside of it, okay? Because you're moving over something and it's a negative value because you're doing it. So you're going from positive to negative, right? So just be careful with stuff like this, because this can give you a bad sign. So now we divide by 2a. That's why I'm explicitly writing this, okay, like that, just so I don't mess up the sign. So now we just add that guy over, so we're left with x final 2 equals x initial, which is our 7, plus a minus v naught squared over 2a. Now, if you squared away your negative, what happens? Are you screwed? Not for this particular problem, right? So you write minus here, and you would write, what is it, 14 meters per second? And then you're squaring that over 2 times minus 6 meters per second squared. These two negatives cancel each other. If you didn't square away the negative, okay, or if you did square away the negative and you have a negative thing here, actually, yeah, this would mess you up. But oftentimes you mess up like this and there's not an initial position. You'd get a negative position for your answer and you'd be like, what's going on there? Okay. But yeah, I apologize. In this instance, this would mess you up and you would get the wrong answer, because you'd be doing 7 minus whatever this guy is, which could still give you a negative position, which would be your clue. But again, be very, very careful. Okay. So 14 squared, this ends up being a negative 196 meters squared, so we're squaring both of these units, over negative 12. The seconds cancel, one of the units of meters cancel, we're left with meters, and this goes away. So 7 meters plus 16.3 meters. So our x final 2 ends up being 23.3 meters. Okay. So this is how you handle types of questions where you have different accelerations going on. If you encounter a problem where you have different accelerations, treat them separately. Do one at a time, where you have periods of constant acceleration, and you'll still be able to solve it, okay, with the tools provided. Okay. We have one more problem to do. A fugitive tries to hop on a freight train traveling at a constant of 5 meters per second. Just as an empty boxcar passes by him, he starts accelerating from rest at a rate of 1.4 meters per second squared. How long does it take him to catch the boxcar, and how much distance was covered? Okay, so the reason this problem is difficult is because this is two independently moving parts. Two independently. The longer you're in physics, the more you suck at spelling, and I'm sure I misspelled a few words already. So two independently moving objects, okay? So we have to track two positions at once, okay? So we need to draw this. This is a very complex system. Well, relatively speaking to what we've been doing. So a fugitive tries to hop on a freight train traveling at a constant 5 meters per second. So let's draw our freight train. Well, maybe if I give him eyes like this. I wasn't sure if it would look creepy or not, but it seems to actually be okay. Let's give him blue eyes. He's not too creepy, right? Looks alright. And he's moving at a constant of v equals 5 meters per second, okay? And because it's constant, a is 0. Just stating this, just so we know. So a cart, okay? Or freight train, v train, let's use train. It's more explicit. Okay. It doesn't seem to have anything else about the boxcar. Okay. The next thing is the fugitive. Just as an empty boxcar passes by him, he starts accelerating from rest at a rate of 1.4 meters per second squared. So we have this guy at the same position because it's passing by him. It's a fugitive, so I like to draw like he's got like a mask on. And then he's got like a, I assume he's like stealing like a bag of cash or something. Okay. Okay, so just as it passes by him, he starts accelerating. So he's going to be moving in this direction, okay, to catch up. And we want to know how much distance was covered, how long does it take him? Okay, so this is where they're going to collide. That's where he's going to hop on. Okay, so he starts accelerating from rest. So the very first thing, I'm going to set a couple things I need to define here. This initial position, when there's a lot of information, I like to just go through and do position, velocity, acceleration, even in my drawings, just to make sure. So X train initial, or we can call it X initial train, I guess. And we're going to call that 0. And then fugitive, we're also going to call 0. How much distance was covered? So X final train, we don't know. X final fugitive, we don't know. But we do know that they will be equal to each other if they've met up. So X final T equals X final fugitive, okay? They meet up, right? Because he's going to catch the train. That's what it says. Okay. The next thing is velocities. We've got our velocity right here. It's a constant. Okay. Our velocity of the fugitive, we don't. He starts from rest. So v initial fugitive equals 0. V final fugitive, we don't know. The last thing is acceleration. A of the train was 0. A of the fugitive is, they tell us, 1.4. So, we've got that information, okay? So now what we need to do, give him a happy face. So now what we need to do is do knowns and unknowns. There's two ways you can do this. You can do knowns and unknowns separately, so you can do two sets. So you can do knowns, train, and then knowns and unknowns of fugitive. And I kind of like doing it this way, just so it helps me further organize the information, because otherwise you have 4 positions, 4 velocities, 4 accelerations, 4 times, or 2 times while you're doing this thing, and it's like a lot to do. So let's just go ahead and rewrite all this information. So x initial train is 0. I'll just call it TR. X final train, we don't know. V initial train is the same thing as V final train, and this was, I think, 5. Yeah. And then A was 0. Okay. And then we have our time. No time. We don't know time. We don't know time on either of these, actually. Okay. So now what we're going to do is the fugitive. X initial fugitive equals 0. X final fugitive, we don't know. But we do know they'll be equal to each other. V initial fugitive is 0. V final fugitive, we don't know. We know the A of the fugitive is 1.4, and we don't know time. Okay. So, how long does it take him to catch the car? So we need 2 things. Time and distance. Okay? And these will be the same for both, right? So we have x final train equals x final fugitive. So I'll just call these both x final. Time should be the same for both as well. Right? Because it doesn't tell us anything different. It's not like it says the train will take this much time, the fugitive takes this much time. Okay. So, we need to pick an equation. 2 equations, 1 for train, 1 for fugitive. So, x final of the train, if we pick x initial plus v naught t, this works. And I say this works because we're allowed to, we have 1 unknown here and 1 unknown here. Okay. And you'll see why this works in a second, even though it's two unknowns, because the fugitive, we're going to use the acceleration version of this equation. So part of the reason this is hard to do, this problem is hard to do, is because we have two equations, two unknowns. But because x final TR equals x final fugitive, we can eliminate one unknown. I'm sorry, we technically have three unknowns because this one's different than this one on first glance. But we eliminate one, and so now it's 2 and 2. So what we're going to do then is we're going to say x final train equals x final fugitive. And so the train equation was x initial train plus v naught train times time equals x initial fugitive. And notice I'm adding subscripts on everything, just so there's no ambiguity. V naught fugitive times t plus 1/2 a fugitive times time squared. Now, all we need to solve for is time. Okay. So the very first thing we can do is we can eliminate a lot of this, right? This is 0. This is 0. They start off at 0. V initial of the fugitive, he starts off at rest, right? So now that very complex formula actually simplifies down to this. So now we can actually just cancel out a time. So V naught of the train equals 1/2 a of the fugitive times t. So now we just solve for time, so we multiply over, so 2 V naught of the train equals a fugitive of the time, and then we divide. So 2, and the train is 5 meters per second. Over a of the fugitive, which was 0. Wait, looked at the wrong one. 1.4. We are going to get units of time because meters will cancel and we'll be left with 1 unit of time, right? Because 1 second will cancel. So time equals 10 over 1.4, which is 7.14 seconds for time. So we've solved one of the things we need. Now, we still need distance. Because, if you recall, the problem asked for how long does it take, and we just did that, and now how much distance was covered. So, we have two equations that we can use. X final train equals x initial train plus v naught times time, or to use this, or x final fugitive equals x initial fugitive plus v naught fugitive plus 1/2 at squared. Okay, we can use either one. So I'll show you the result of you using both, and it should give you the same answer. So x final train, and that's because we set these equal earlier, that it gives you the same. V naught times time. Our V naught was 5 meters per second times 7.14. And this gives us a result of 35.3 meters. Okay. And if we plug in this guy, our x final fugitive, we can cancel the things, right? This one was 0, this one was 0. One half 1.4 times 7.14. And this also happens to equal 35.3 meters. So they're the same. Okay. And so this problem is now solved. I do want to kind of mention, I know this problem is very complex, especially relative to the other ones. I wanted to do something difficult for you so you can see just how complex this can get. But I will say, if you encounter a problem ever that has two things happening at once, you're gonna end in it's like, oh, where did they meet up or something. That's essentially the flow will be how this one works, where you have two independently moving objects, where you have the train and the fugitive, okay? It'll work the same way, where you just link the positions or you link the times. And so if you have a hard time with this sort of problem, just rewatch the video. Hopefully it works. Hopefully the cute little train here helps. I think it's funny. I like the little guy with the, you know, the thief or whatever with the money bag. But it is a difficult problem, and it's harder than the other ones we've done because of really a couple reasons. Number one, we're dealing with more than one unknown. Every other problem we've done so far has just been a single unknown. But it also is difficult because you have to link them up, and we've never done that before either. So try to acknowledge where your uncertainties in the material lie, and that will help you figure out how to solve them in the future. It's like, well, I don't know this very specific thing. Acknowledge why you don't know it, and then try to learn from it, and then that will help you improve. Okay. So I'll go ahead and just end right here with the little guy appearing. I like these drawings. Anyway, thank you for watching, and I'll do some more examples in the next one. Do vertical examples. Okay, thanks for watching. Bye.